Hi everyone. Good morning, good afternoon, good evening from wherever you are from in the world. So, welcome to our Rising Star Symposium series. We are a special interest group in AI and ML security, AI and ML in security from IEEE Technical Committee on Cognitive Networks. Our president, our special interest group chair is Professor K.P. Subbalakshmi from Stevens Institute of Technology, and I myself, Devashi Roy from UT Arlington, Professor Moinul Hussain from George Mason, and Professor Hanif Rahabari from Rochester Institute of Technology. So I just have a few slides to talk about our group and our series, and then I will hand it over to our speaker, our rising star today. So about our group, we are a member. We have an existence in LinkedIn, and also we have a website. So please, to get to know about our activities, please join our LinkedIn group. So far, we have more than 600 members. You can also connect with us via our emails. And all our recording talks are always available online. You can get it from our website. That website is here somewhere, I think. Okay, so what we do in the past, from the pandemic time, we had organized a few virtual seminar series of different distinguished members and researchers in the area. These are also available in our website. And yeah, this is our website. You can find it and our YouTube channel. Next. So this is a new initiative from the group. We are doing this from last 1 year. This is an opportunity to hear from the emerging scholars or stars. We call them the rising stars of this research area. They are mainly senior PhD candidates or postdocs to present their work to the broader audience. So we request our rising stars to keep their talk within 45 minutes and prepare it as a job talk format and mainly to interact and engage with audience. So these are a few of our rising stars from previous years. Many of them are now established in the academia. They have gotten different academic or industry jobs. So I'm not going into details of all of them, but we had almost 10 of them, and this is our 11th talk. So overall, our logistics of the talks are everyone is muted on the entry, and please stay muted, but please don't hold off your questions. Please type in them whenever you are having questions. Please type in them in the Q&A or the chat section, and then at the end of the talk, our moderator will be moderating those questions. We will be moderating those questions. So with that, let's just introduce our rising star, Talip Tolga Sari. He's a PhD candidate at Istanbul Technical University from Turkey. His research focuses in next generation mobile and ad hoc networks and MAC protocols, task-oriented communications. He received multiple awards, including the Best Paper Award, Master's Thesis Competition Awards, Outstanding Achievement Award in Education and Teaching for research assistants in his organization. And he is author of more than 15 peer-reviewed research papers, both conferences and journals. So with that, I will stop, and Tolga, the floor is all yours.
Thanks, Professor Roy and Professor Hussain. It's a truly honor to be here and give this talk. So share my screen. Hopefully everyone can see. Okay. So hi, I'm Tolga. My talk is titled Task-Oriented Communication and Digital Twin-Enabled Wireless for Next Generation Ad Hoc Networks. So before we start, let me briefly talk about myself. So I did a double major on electronics and communication engineering and also computer engineering in Istanbul Technical University. So I wasn't sure about which one to pick. So I just figured, let me just do both of them. And it's been a fun challenge. I did my master's then in computer engineering. And currently I'm a PhD candidate and research assistant in Istanbul Technical University. And I'm also a member of ad hoc networks and systems research group under Professor Gökhan Seçinti, which is my thesis advisor. And my thesis is about semantic wireless communication framework for ad hoc networks. And I also had an opportunity. I was also had an opportunity to be a visiting PhD student at University of Vienna, University of Bologna, and recently at University of Texas Arlington with Professor Roy. It was a very fun experience for me. And let me start the talk. So this talk structure is that first we are going to briefly talk about ad hoc networks, then we will talk about their challenges, and then we are going to slowly build up how we can use task-oriented communications for them and digital twins to make them much more better. And we will talk about how we do coordination in ad hoc networks and conclude the talk. So hopefully I will not bore you too much. So let's start. So what are ad hoc networks? So in ad hoc networks, the nodes are the infrastructure itself. So there is no infrastructure, and the nodes have their own traffic, and also they carry each other's traffic. And since these nodes are moving, they have to communicate through wireless communications. And due to the nature of the routing algorithms and the density of these networks, as the central nodes experience more and more traffic, they also experience more collisions. And since they are on the way of most of the communications, as the density increases, the performance of the whole network drops. So these collisions decrease the efficiency of these networks. And this issue is also multiplied as the long-range communications happens in these networks, which require multiple hops through the nodes. And for this, what is our solution? So we first need to understand that just making links faster for these networks doesn't ultimately create better networks, because the interference problem grows faster than the link capacity we can provide to these networks, and the density just collapses, increase the interference and the collapses the network. So for this, we take a two-path approach. So one path is we use semantic communications to control the traffic that we require to complete certain tasks, to reduce the traffic requirement and relax the network. And for the digital twin part, we model the network and we model its channel to enable better coordination, such that we have less overall interference, efficient communications, and ultimately much more scalable ad hoc networks. So let's first start with the levels of communication. So in his work, Shannon defined 3 levels of communications. And let's start with the upper one, so the level C. In the level C, in the effectiveness level, we ask question, does the communication achieve its tasks? And we are concerned with the task achievement and feature selection and fabrication. So ultimately, we ask questions like when we should communicate, when we should send certain packets. What is our common knowledge between us and the target, and which information is significant when. At the level B, then we focus on how well we convey the intended meaning and how well we represent these features and how we can recover it. So the question here is, does the symbols we send, does the symbols we select say what we want to say, represent, or transmit which features we want to transmit? And these two levels, level B and level C, is intertwined, and we cannot separate them from each other. They are scenario and use case dependent. And lastly, at the level A, the technical level, we are all familiar with. We are just concerned with sending bits, and we don't care what's inside them. We don't care whether the sender and the receiver has the same context, they share the same common knowledge, or what time of the day, or how well a task being completed. So let's start with how we can use this task-oriented communications to have better data links. So our target here is how traditional ARC works. So ARC means automated repeat requests. So this is been around a long time. So when we are going to send a frame at the data link layer, so we pass the contents of this frame through a function that spits out a number, a cyclic redundancy check number. And we send this frame, and the receiver receives it, and it also does the same. Calculations, same cyclic redundancy check. And if the checksums are equal, then there is no bit error. There is no bit error. And it sends a ARC to let the sender know it received the packet correctly. But if there is a single bit error, then the CRCs will not match and it will fail, and it will toss the packet to the garbage. So this sometimes wastes like close to perfect packets. Imagine you are sending an image, right? If there is a single pixel error in it, for certain tasks, I think you can get away with it, right? For example, a camera recording. So how we can improve this? Our idea is introducing semantic arcs. So what if instead of checking whether all bits are correct, we checked whether all semantics we want to send are present and detectable? So basically, on the left, we have image data we want to send, and we are concerned with letting the receiver know where the car is in the road. So we append a semantic header saying that after decoding this image, you should see a car around these coordinates. And if the receiver can decode where the car is, then we are good to go, despite having bit errors. So if we take a closer look, so we append the semantic header and send it. And the receiver has, of course, some bit errors and cannot understand where the car is through its machine learning algorithms. So it sends a semantic arc saying that I see no objects, but I should have seen a car, right? Then the sender only sends the relevant part where the important feature is to the car, to the receiver. So then the receiver receives it and it combines it with the previous transmissions, and then it says, okay, now I can decode where the car is. since the transmitter is now required to transmit less information, it relieves the bit budget, right? For example, if it was required to transmit whole image, for example, 10 kilobits, now it is now required to transmit 1 kilobytes of data, for example. And we are now saving 9 kilobytes of data, and we can use this relieved bit budget to use stronger forward error correction to let the receiver receive the important parts of the image, even if the channels is poor. So let's go over our evaluation setup. For this work, our objective is object detection, and we use YOLA 11X for object detection, and we have for the modulation we use 16 QAM for the payload and QPSK for the semantic header and semantic arc. And again, for the forward error correction, we use 1/2 for payload and 1/5 for the semantic header and arc. And we use a simple channel of AWGN, and the data set is Udacity self-driving car. And for the performance metrics, we use an intersection over union with 0.5 detection threshold. So, for example, this was where the feature has to be detected, but if the receiver detects it like this, we consider this as not detecting correctly. So the detected features has to be close to each other. And we also look at the total transmitted data size. So here's an example. So for SNR of 2 dB, on the left we have original image. At the initial transmission, the receiver can't decode anything, so it asks for where the important features are with semantic arc, and it can now receive something. So the important thing to notice here is the channel is bad here, and resending this initial transmission again and again and again won't make a difference at the receiver's end, and it won't be able to detect where the cars are. But using this semantic automatic repeat requests, now we can at least send some important information to the receiver and make it detect where the important features are when the channel conditions are bad. So here's another example for now this is SNR is 3. So here, after initial transmission, the receiver can detect some objects, and it doesn't ask for this object. And now it only asks for the potted plant in the middle and the traffic light on the right. And here is another example with 4 SNR. Here, if you can see, there is a bit error rate here, bit error rate here, bit error here, and some bit error here. So the traditional method would have tossed this image to the garbage. But the receiver can complete the task, right? It can see where the cars are, where the persons are. And now it doesn't ask for a retransmission because it can recover the important features. And if we look at overall results, so on the left, we have the overall intersection over union. So this shows us how the bounding boxes are correct. And on the right, we have total sent data. And so in the traditional arc, sending the picture again and again provides a marginal improvement. But with semantic arc, we can now recover the important features, and we use the fraction of the data required. So we are using stronger error correction. We are having a much more larger overhead. But since we are required to send less, overall we are saving bits, and we are also enabling communication in harsh channel state. And as the SNR increases, as the channels get good, then we don't require retransmissions, and we see no improvements. So,
Talib, I have two questions, if you don't mind.
of course.
So first one, your paper about feedback by relevance.
Mm-hmm.
I don't see it. I don't know how to get it.
Oh, so it's under review.
Okay.
But I think so. If you send me an email after I can send you.
Okay, then please put your email on the chat.
Yeah, of course. Let me put.
Yeah. The second issue is what you described in this presentation. I have seen something similar from others under the name of a qualitative communication, where the sender doesn't send everything, they send some of it, which is relevant to the receiver.
Mm-hmm.
So I'm not sure if you have seen their papers. It's under the name qualitative communications. If you send me, if you put your email on the chat, I can send you stuff.
Yeah, I have put it in the chat, but I haven't seen that paper. But in this work, the ultimate proposal is that we provide a way that we can put semantic information and important features in the data link, in the frame, and we provide a way that the transmitter and the receiver can reach a consensus about important features. So this paper is not just about sending the bounding boxes of the images, but it's about how it can recover if the channel conditions get worse or if there is an error. So
Yeah, that
method.
is.
Hmm,
Yeah, let us. I will send you an email.
okay,
I will talk about. Thank you very much.
thank you for the question.
Thank you.
So moving on, now let us look how we can use semantic communications to control the traffic in the network. So our use case here is localization using ultra-wideband communications and using ultra-wideband communications for the localization. So ultra-wideband communications allow us to transmit narrow pulses that is quite resilient to multipath effects that then allows us to measure the time of flight between the sender and the receiver really well and therefore do localization. But in order to have really accurate measurements and in order to track the location well, we require high beacon rate, so high communication rate. And this then causes these localization frameworks to not scale well, because if all of them require high communication rate to be accurate, then we can't scale them. So it's semantic flow control. We provide a way to throttle this communication rate using a task-oriented approach. So this is our proposed system. So this is quite standard localization framework. we have anchors, ultra-wideband anchors deployed in the corners, and the mobile tag transmits an ultra-wideband communication and ultra-wideband beacon, and these beacons are picked by the anchors, and then they do localization. So whether for this work we are using time difference of arrival, but there are different localizations. And the idea here is, so we are using a Kalman filter. This is again a very basic and very well-known filter, but the idea is this filter uses both predictions and it uses our measurements. And it chooses whether to trust more whether the state predictions or whether trust more on the measurements. And our idea is, if the Kalman filter is in a state that it can predict the movement really well, so the state estimation error is low, then our system sends a semantic feedback to the mobile tag and says, okay, I can track you really well. You don't have to speak too frequently. And overall save communication resources. So for example, if I talk really, really slowly, you would say, okay, Tolga, speak faster, we can understand you. It's kind of similar approach to this. So the protocol is, we have our state estimation error here. And since this is a pretty volatile, it changes rapidly, we have to be very certain about our confidence of prediction of the moment. So we first pass this through a low pass filter and increase our confidence, and also use a sigmoid function to calculate how much communication rounds that the mobile tag should skip. And then we also have a concept of warm-up counter here. So we can have some lucky rounds where our state estimation error is pretty low, but then it can change rapidly. So we say, okay, we should at least wait for 20 measurements or like 10 measurements before we suggest skipping some communications. And if then we go to the performance evaluation, and we do this in our open source simulator, which is based on Python, basically, and we measure the localization error and the communication effectiveness. The important thing is, so we defined effectiveness metric here, and it's task completion quality over the number of bits we have to send. And for this work, the task completion quality is 1 over average localization error. So if the localization error is low, then we complete the task well. That's the idea. And if we complete the task using less number of bits, it's even better. We also included how the inertial measurement units data would affect the overall performance. So the IMU here also provides us the mobile beacons velocity and acceleration, and the Kalman filter can use these to make better predictions, so resulting basically more confidence and resulting less communications. And for example, here is a demo example scenario. On the left, we have a traditional communications where we constantly communicate regardless of the error, regardless of our prediction performance. And on the right, we have our semantic flow control. And when this blue uncertainty line turns to green, it means that the communication stops and we are now relying purely on the estimations. and we are saving up resources. And if you look at the results of this demo, on the top, we have localization error, which is in meters. On the middle, we have uncertainty. And on the bottom, we have communications per rounds. And one thing to notice here is when we send the semantic feedback, our communication cost doubles, right? Because we have to use the channel. But following that, we save resources, and we still be able to complete task, and we make the network more scalable while not sacrificing too much for the task completion quality. So if you look at the results, so we compare normal Kalman filter with our semantic flow control, and we also compare addition of inertial measurement unit. And as you can see, we have similar task completion quality and localization errors, but we have increased communication effectiveness. So this means that we can complete the tasks in a similar way while requiring less number of communications. So let's now move on to how we can use digital twins. And one approach with this is we use ultra-wideband enabled digital twins for Wi-Fi 7. So before we start, we have to remember some techniques. So first one is coordinated beamforming. So this is introduced with Wi-Fi 7. And the idea here is, compared to the normal beamforming, when we are selecting which beam to use, we are now also considering the neighboring Wi-Fi networks. So, and we try to select a beam that provides high signal strength, but also lower interference to our neighboring network, such that we cause less collisions, less interference, and overall be more effective. The next thing we should know is clear channel assessment. So, and in Wi-Fi 6, they introduce an enhanced CCA mechanism, which allows us to change carrier sense thresholds based on whether the transmission source is in our network or outside our network. So how this works is, if we hear something in our band, but that transmission's power is less than our carrier sense threshold, then we don't care about it. We just ignore it. But if it's higher than our threshold, then we back off and wait for it to end and just wait. So with dynamic clear channel assessments, we select lower thresholds for the same network traffic, and we choose higher thresholds for the different network traffic. The idea here is we can ignore our neighbor's traffic a bit more, because it's probably the access point is probably using a good beamforming, and if we even caused interference, the SINR the SINR won't be that bad, and still they will be able to recover some stuff. But the selecting this threshold is a tricky part. And actually, for both of these methods, we have to know the channel well. And that's where the existing channel models don't help us too much, especially in the indoor environments, because most of the models are stochastic and they consider the distance and the height difference, but they don't consider scene's geometry and how the signal propagates and bounces and refracts. So we require ray tracing based channels that consider the scene, consider how the signal reflects, how it refracts, to model these interference issues well. And for this, we propose ultra-wideband assisted digital twin for Wi-Fi 7. So we again deploy ultra-wideband anchors, and we equip the stations with ultra-wideband chips. So for example, your mobile phones, if they came last 4 or 5 years, already have an ultra-wideband communication chip. So they are able to send ultra-wideband beacons. And since we know where we put the access points and where we, through the ultra-wideband communications, where are the stations, we can model and we can create a digital twin of the network. We just need to have an environment model, and we can use tools like Sionna to model the channels and model the impulse responses between each device and make informed decisions on the channel behavior. And looking in much more detail, so here the access points have a codebook that they choose from, and they choose what kind of beam that they are going to use. And since the access point do not move, we can calculate these coverage maps for each beam offline and just upload these coverage maps. And when they know where the stations are, they can just select the best beam index, right? Best beam index that provides best coordinated beamforming performance, and be done with it. And for the dynamic CCA, we look at when a station hears a foreign color frame, it checks source to destination RSSI, and it calculates then how would it affect the SINR at the target of that message. And if it transmits and the SINR is still high, it doesn't care, it transmits. And these are possible with ultra-wideband assisted digital twins. So if you look at how the sequence happens is, in beforehand, the access points does coverage map calculations. We do this offline and we upload them. So they know if they choose beam 1, how it will light up the environment, basically. And when the stations send beacon to the position tracking system, PTS, we use time difference of arrival solver, and then we feed back the station locations to the access points. Then they do coordinated beamforming optimization. And when then access points send data, sometimes the stations can hear it. For example, station 2, which is in network 2, hears the transmission of access point 1. And then it does dynamic CCA calculations and says, okay, if I transmit, would the SINR at the access point 1, access point 1 and station 1 will be low or high. If it's still high, then I can transmit it. That's the idea. And if we look at the results, so these last two are our digital twin-based approaches. And we see that overall, we are increasing the overall aggregate throughput because we are using the network much more efficiently. If you look at on the right, this is average contention window size. So the contention window means that it's measured with the slots. And for example, if it's on average 40, this means that the nodes in the network has to wait on average 40 slots in order to transmit, or they have to back off 40 slots in order to transmit. So if the contention window is lower, it means that there are less collisions in the network, and the overall less airtime is being wasted. Okay, so now let me move on to the last part of this talk, which is a coordination in ad hoc networks. So I am going to present a use case in one of our research, which is remote environmental monitoring. So the challenge here is the environmental monitoring requires continuous sensing across a really large area, and these areas are also remote regions, so they don't have an infrastructure. And if we took a traditional fixed sensor network approach, this will require us to deploy many gateways, and because the sensors on the ground has poor coverage, because the terrain is uneven, and as a result, they can't have line of sight links. So the overall, each gateway's communication range is smaller. And also, if we treat all sensors equally, we will again waste resources, because some sensors measure data or processes that change fast, and some sensors measure data that change slowly. So for example, if you are going to measure the soil pH, which changes really slowly, you don't have to measure it every millisecond, right? It changes slowly. You don't need to waste resources. So for that, we propose UAV assisted edge intelligence. So as UAVs are flying, they have line of sight links, and they can cover larger areas and adapt the changing conditions. And we use edge intelligence to make on-site decisions without relying on the cloud, right? Because if we have to speak with the cloud to make decisions, then we are wasting wasting time, because we will have increased latency. So this is how it looks like. So again, we have a common UAV deployment that measures the and probes the sensors deployed, but we also have edge intelligence in their flight computers, and they do anomaly detection, basically. This is our use case. But when we are calculating their trajectories, we are considering the process volatility. So if the process under a sensor is volatile or known to be volatile, we visit it more often. If this process is non-volatile, then we visit it less. Because in the end, what is our goal with the sensing? We are trying to track a remote process. So if we know that it's going to stay same for 10 days, we don't have to measure it continuously hourly or every second. And this allows us to relax our trajectory constraints and overall make the deployments more scalable. So I don't want to get into like I don't want to get into more details, but the idea is we model the processes as Wiener process. And so we looked at what happens the point we measure, the second we measure, and as the time continues, how wrong our measurement. So for example, if we measured here, right, as the time moves on, we think the process is behaving like this, but we have this square error, right? This process error that we have. So it turns out the area here and the difference here is also a Wiener process, right? Because this is the definition of the Wiener process, and we are going to use this property to calculate how much we should track a process or not. So the idea basically is when we calculate that the square errors area, it's combination of process variance times the age of information area. And if we divide this age of information area to overall time, this results in average age of information times the process variance. So what this means is, if we know our deployments, our trajectories resulting age of information and average age of information, we can estimate how will the estimated mean square error will be. So we can say, okay, when we are measuring the temperature, we are going to have error of 0.2 Celsius on average for this age of information, for this average age of information. And for this work, we use these values for different processes. So we have air temperature sensor with mean of 15.1, and the process variance is 0.1. And for example, we have soil pH sensor, which has mean of 6, and the process variance is 0.0001. So we shouldn't treat these sensors equally, right? We can measure the air temperature more compared to soil pH and still have similar errors, similar estimation errors with them. So if you look at the results, we compare 3 deployment strategies. One of them is just random trajectories. We deploy UAVs randomly, and they probed the sensors. The other one is age of information optimized deployment. So we do the deployment, but the deployment tries to optimize the overall age of information regardless of the underlying process. And the last one is our expected mean square error optimization. So this tries to minimize the resulting expected mean square error of a deployment. And expectedly, if you are optimized for age of information, you will have lower age of information. But our method has lower mean square error. So yes, overall, we can have more age of information, but we have less age of information for the sensors that matter or the sensors that require it. And ultimately, if you look at F1 scores for anomaly detection, our deployments perform better because our deployments track the underlying processes better, and can catch the anomalies more accurately. And to conclude this talk, we require task-aware wireless networks. So we should prioritize crucial features and task success instead of raw bit correctness if we want to make the network scalable. If we have to have adaptive designs that provide us global coordination. And we require overall task-oriented networks that is more scalable and that they consider that they optimize for the real-world applications that allows us to make them more scalable. So the next generation networks will not only measure or no longer only measure success in bits per second or lower latency. They will measure how they accomplish tasks well and how much features they deliver. And here's my list of publications throughout my PhD. And thank you for listening. And if you have questions, I'm happy to answer all of them.
Yeah, thank you for the presentation, Tolga. So we have one question. The first question is from Hesam. How semantic communications can improve TCP performance?
Okay. Oops. Sorry. So that's in that regard, they are not entirely compatible because TCP is for reliable data transfer and it guarantees that there will be no bit errors that when we send data. But for the semantic communications, we say that in order to complete certain tasks, we tolerate some errors. So in that regard, TCP is not entirely compatible in order for the tolerating the bit errors, but we can come up with smart feature selection methods and smart feature compression methods that allows us to transmit less information in order to complete a task. So with semantic communications, you can reduce the amount of data you need to transmit, but if you are going to use TCP, it has to be reliable. So these information you send has to be reliable.
Okay.
So they are compatible but not entirely.
So maybe we can say it's more complementary because TCP
Yeah.
actually consumes more resources to make sure that the reliability and the in-order delivery. But sometimes we actually do not need that level of reliability from semantic perspective.
Yes.
That's what you're, okay. So it more complements the TCP.
Yeah, we can say that, yes.
Yeah. All right. So the next question is from Boniface. Did you analyze the complexity of modeling the digital twin of physical networks by comparing the ray tracing channel models and statistical ones?
So for our digital twin work, for this work, we compared them with the traditional methods. We didn't compare them with existing channel models, but in one of our in one of our unpublished under review work, we compare them, but not for this work.
Okay, all right. So the next question is from Hassam. Can we use feature-aware automated repeat request for other networks such as wireline networks?
So I don't know what they mean by wireline. Do they mean like Ethernet or?
So, Hassam, if you're there, maybe.
Wireline is like any net. It's not wireless network, not mesh, not wire, not wireless. Use
Mhm.
wire.
Okay. So it depends on this depends on the data link protocol that they use. So if the MAC protocol or the data link protocol has automatic repeat requests, then yeah, of course this can be used. But as far as I know, so for the latest deployments for the Ethernet, they removed they don't use automatic repeat requests. So if there is an error when you are transmitting a frame, the switch just drops it, and the error correction and reliable transfer is guaranteed by the TCP. So if a frame drops, they don't care. But if another protocol that is based on wire uses these automatic repeat requests, then this can work. But again, if we are going to use wires, then we are expecting we don't have channel contention that much unless we are using some kind of bus. So I personally don't see the benefit, but it's possible.
So if we use Ethernet,
Mm-hmm.
the data link layer doesn't have automatic repeat request, but LLC protocol on top of data link, it is part of layer 2. It has ARQ. It has an option to support ARQ, but it is end-to-end at layer 2. So
Yeah.
what you are saying that this ARQ you're talking about is at the link level, hub by hub level, right? It's not end-to-end,
Yeah,
correct?
it's it's hop by hop level. Also, it's cross layer. So this ARQ requires the receiver to decode the image, process the image, extract the features, then send the ARC. So yeah,
So
it's
the transmitter and the receiver are in the two ends of one link,
yes,
one hub, and
yes,
it is all at layer 2.
yes.
The semantic the other proposal which I sent you over email, which is they call it qualitative communication. It
Mm-hmm.
actually exists on the at IP level, you know, or
Mm-hmm.
complement TCP, and it is end to end. Like TCP, it's end to end. It is not hub by hub. That is major difference between what you are proposing and what those guys propose. You are hub by hub, and they are talking about end to end, like TCP.
Yes, and again, our approach is targeted for the harsh environments or like harsh channel conditions. So if we cannot communicate at all using the traditional methods, we propose, okay, let's change how we send these ARQs such that we can at least enable some kind of communication if the channel is bad and at least complete the task.
I got it. So the unmanned vehicles example that you mentioned also use this feature aware ARQ, correct?
No, it looks at this. It looks at how the underlying processes behave for each sensor, and it then does trajectory optimization. So This is
two
targeted
different
for
yeah,
ad hoc network,
yeah.
ad hoc network coordination.
Yeah,
So this,
two different subjects, so it is
yeah,
not related to feature aware ARQ. I got it. Two
yeah.
different things.
So
Yeah,
so the idea is we are trying to improve the ad hoc networks by approaching it multiple directions. We use digital twins. We use task-oriented communications. And try to make them much more scalable. Because
excellent.
if we just say, okay, we just have better links, it won't work.
Yeah,
And as the increases, the network becomes much more unmanageable. So
this is very good. This is very good. Your website has all the papers, all of your papers, right?
yes,
Excellent. Thank you very much.
thanks
Excellent presentation. Thank you very much.
so much.
Yeah, I do not see any other questions in the chat. So we are already 5 minutes over our timeline. So thank you, Tolga, for receiving our invitation and presenting the talk. It was a nice talk. And as you can see from the audience, it has been very interactive. So best of luck for your future. All right.
Thank
Okay,
you. It's
take
been
care.
an honor. Thank you for giving me this opportunity. I really enjoyed it.
Yeah.
Thank you, everyone.
Yeah.
Thank
everyone.
you. Thank you very much.
Thank you. Bye.